Okay, in this video we'll be continuing with our level 3 circular motion. More specifically, in this video we'll be going through banked corners. However, just a quick reminder, whenever we have a case where we have an object moving in a circular path around a corner, we know that there must be a net centripetal force acting towards the center. We know that this force is not a real force, it is provided by another force. These forces could be tension from a string, friction from, let's say, tires in the road. And in our Newton's gravitation video, we found that Fg could also be the force that provides the centripetal force. So now in the case of a banked corner, this is actually a different scenario. The centripetal force is provided by the horizontal component of the normal force. So what I mean by that is if we have a guy standing on the ground like this, we know he's going to have a weight force going down, and therefore he also must have an equal and opposite normal force acting upwards, and that is, again, at right angles to the ground. That's why it's called the normal force, because it's normal to the ground that he's standing on. So if we take that same guy and we put him on a little slope or a banked surface, and we make him stand up here, again, his weight force is still going to act directly down, but now his normal force is going to act up here, because that still has to be at right angles to the surface. So if we take a case where we have a car now on a banked surface, right? So this blue thing is the car, and the car is going into the page. This angle is theta. We know that the car is going to have a weight force directly downwards, and also there is going to be a normal force, just like this dude over here. Now in this case, Fc is provided by the horizontal component of the normal force. And what I mean by that, if we break up this normal force into its components, we would have Fny, so the normal force in the y direction, and we would also have Fnx. So Fnx is the component of the normal force that provides the centripetal force. Now for accuracy purposes, this Fn right here should be much larger. The reason for that is because the component of the normal force in the y direction is equal to the weight force. And because the normal force is also providing the centripetal force, the normal force must be much larger than the weight force. We can also see this in our vector diagram. If we draw our weight force down and we draw our normal force up here, we can see that we get a net force in this direction, and that is indeed our centripetal force. This theta right here is located just over there. Now from this vector diagram we can get three equations. The first one being that Fn cos theta is equal to our weight force. The second one being that our Fn sine theta is equal to our Fc. And the third one being that our weight force, tan theta, is also equal to our Fc. So these equations here are just derived from some basic trig from this vector diagram right here. Okay, so we can move on to a question now. A 1200 kg car on a 20-degree banked road turns a radius of 85 meters without friction. Now remember, no friction is needed when we go around a banked corner because the centripetal force is not provided by friction, it's provided by the horizontal component of the normal force. What speed is needed for the... that should be car. What speed is needed for the car to stay in the middle of the road? Now, in order for the car to stay in the middle of the road, the normal force in the y direction must be equal to the weight force. If the normal force in the y direction is greater, then the car will move up the bank, and if it's less, it will move down the bank. So it needs to be the same in order for it to stay in the middle. So we know our weight force, tan theta, is equal to our centripetal force, and we also know that mv squared over r is also equal to our centripetal force. And therefore, Fw tan theta is equal to mv squared over r. And therefore, mg tan theta is equal to mv squared over r, we can cancel out our m's, and we get g tan theta is equal to v squared over r. And therefore, gr tan theta is equal to v squared, meaning that the square root of gr tan theta is equal to the velocity. Now we know our radius is equal to 85 meters, and we know our theta is equal to 20 degrees. And so the square root of 9.81 times 85 tan 20 degrees is equal to 17.4 meters per second. There we go. So a few more examples where you can see this same type of scenario is where we have a plane. This is a plane. That's a plane flying through the sky. And as the plane turns, it kind of banks itself. And so we get an angle right there, theta. And it's the same scenario. We have a weight force going down, and we have a normal force coming up here. That's a W. That should be an N. There we go. Another scenario is where we have a conical pendulum. So basically a pendulum with like a ball, and the ball swings in a circle. As you can see, there is a weight force down there, and there is a tension force provided by the string, which results in an FC. So these are just a few other scenarios which the same logic applies, and therefore the same equations apply. These ones right here. And so it's the same step-by-step process in how you solve it. And that should be good. If you have any other questions on horizontal circles or banked corners, just let me know in the comments and I'll make a video on it maybe. And yeah, sweet.